Assalamualaikum warahmatullahi wabarakatuh. My name is Mohamed Adib Afnan bin Abdullah.
Hi and Assalamualaikum. My name is Khairina binti Mohamed Habib.
And my name Nuris Nurfalah binti Mohamed Khari.
Assalamualaikum everyone. Welcome to our group discussions for assignment 2, task 2. My name is Nuris and I will be leading today's session. The three of us have each chosen a real world problem that uses vector mathematics, and today we will take turns sharing our findings. After each person presents, the other two members will give feedback. We will look at what was done well and what could be improved. Please be honest and constructive. This is how we all grow. We have exactly 30 minutes, so let's use our time wisely. Here is a quick overview of our topics. I will go first and talk about how vectors are used in smartphone touchscreen technology.
After you, we continue with present about vector navigation during a hiking trip at Fraser Hill.
Okay, I will share my work on how vectors are applied in precision agriculture using GPS, fertilizer, truck. Let's get started.
So, my chosen real-world problem is about how vector mathematics works inside a smartphone touchscreen. Every time you tap, swipe, or pinch your phone screen, the phone is actually solving a vector problem in real time, and most people have no idea. Under the glass of the screen, there is a fine grid of electrodes. When the phone is on, it sends current through what are called drive lines. This creates electric field vectors that have both direction from positive to negative electrodes and magnitude, which is the strength of the electric charge. When your finger gets close to the screen, it acts as a conductor. It pulls some of the field strength toward it, which changes the magnitude of the vector at the specific x and y coordinate. That change tells the phone exactly where the touch happened. However, there is a problem. Your finger is physically much wider than the tiny wires in the screen. So, one tap activates a block of about 20 to 50 intersections at the same time. If the phone just picks the intersection with the strongest signal, the cursor will jump around and feel very inaccurate. To fix this, the phone uses a weighted position vector. It treats each signal strength as a weight and then uses the centroid formula to find the exact center of the touch. P final equals the sum of Wi times Pi divided by the sum of Wi. This gives sub-pixel accuracy, meaning the phone can detect finger movements smaller than 1 mm even when the wires are 5 mm apart. When you swipe, the phone calculates a displacement vector. Delta equals Pn minus P star. The direction of this vector tells the phone which way to scroll, and the magnitude tells how far to move the page. When you use two fingers to pinch or zoom, the phone tracks two position vectors, A and B, and finds the distance vector between them. V distance equals B minus A. If the magnitude of this distance vector gets bigger, you are zooming in. If the angle between them changes, the screen rotates. The main advantage of using vectors here is that the phone can handle detection, position, scrolling, and rotation all at once using different type of vector operation. The main limitation is that standard globes block the electric field completely. No vector can change mean No vector change means no touch detection. This is exactly why touchscreen friendly gloves use conductive fibers. That is my presentation. I would like to hear your thoughts now.
Okay, thanks, Nuris.
Okay, thank you, Nuris. I really like how you connect for different types of vectors, like the electric field vector, the weighted position of vector, the displacement vector, and the distance vector, all within one real-world example. That shows a very thorough understanding of vectors and makes the report feel very complete. Most of us only use one or two vector types in our reports. One thing that I think you could improve is the calculation section, which is you need to explain the centroid formula well. But there is no word example with actual number. For instance, if you show Trinity section with a specific signal, width and coordinates, and then calculate the final position step by step, the mathematics will be much more visible. So right now, it is explained in words, but we cannot see the actual working.
Okay, thanks for Khayra. And I agree with Khayra because when I just look work PB Nuris, another strike I want to highlight is your topic choice. Smartphone are something all of us use every day, so your audience can immediately relate to the problem. It's made vector feel very relevant and modern. It is a smart choice because it shows that vectors are not just for textbook, for our outdoor navigation. They are literally inside the device in your pocket. So my suggestion for improvement is the limitation section. You mentioned that standard glove block the electric field, which is a good point, but I think you could go deeper. For example, what happens when the screen is wet are when you use a thick phone case. There's a real situation where the vector interaction is affected, and editing them would show that you have to think carefully about the practical challenge, not just the mathematical one.
I understood. Thank you for both of you. Those are really fair points. I did feel that my calculation section was a bit thin, and I now agree that showing a full numerical example using the centroid formula would make it much stronger. I will also expand the limitation section to include wet screens and thick cases, since those are real situations people face every day. I appreciate your honest feedback. It helps me see my report from a different angle. Thank you. So next.
Thank you. My real problem is about a hiker navigation through a Fraser Hills Nature Reserve using a compass and vector mathematics. In many parts of the forest, the terrain is rough and there are obstacles like rivers and dense trees. So the hiker cannot travel in a straight line. Instead, the journey is broken into two straight legs, which means the distance. As you can see from the diagram is here, leg 1 is 5 kilometers at a bearing of 060 degrees, and leg 2 is 7 kilometers at a bearing of 120 degrees. If we simply add those distance, we get 12 kilometers, but that only tell us the total path length. It does not tell us where the hiker actually ends up to the real final position. So we need to use the vector decomposition and addition to find the total distance. Since compass and bearings are measured clockwise from the north, each leg can be broken into an east component and a north component, using trigonometry. The east component is we assume that d times sin theta, and the north component is d times cos theta. For leg 1, at here, vector E has an east component of 5 times sin 60, which is equal to 4.33 kilometers, and a non-component of 5 times cos 60, which is equal to 0.5 kilometers. So vector A is 4.33 east and 2.50 north. For the distance 2 or leg 2, vector B has an east component of 7 times sin 122, which is equal to 6.06 kilometers, and a north component of 7 times cos 120, which is equal negative 3.5 kilometers. The negative sign tells us that hiker is moving to the south, not north. Adding both vectors give a resultant of 10.39 kilometers east and 1.0 kilometers to the south. By using the Pythagoras theorem, the magnitude, the straight line of displacement is the square root of 10.39 squared plus 1.0 squared, which is equal to 10.44 kilometers. For the direction, I calculate the angle using inverse tangent slightly to the south. A tangent of 1.00 over 10.39, which is give 5.5 degrees. Since the vector points east and slightly to the south, the final bearing is 19 plus 5.5, which is 095.5 degrees. So, although the hikers walk 12 kilometers, the actual displacement is only 10.44 kilometers at a bearing of 95.5 degrees, just slightly south of due east. The key advantage of vector here is that they give both distance and direction, which is a simple addition cannot do. The limitation is that this model assumes flat terrain and a perfect compass reading, which is not always realistic. That's all my presentation.
Okay, thank you, Khayra. A strong point in your report is that your problem is very easy to follow. You choose a scenario that most people can picture in their heads, someone hiking through a forest, and that makes the mathematics much easier to understand. Your step-by-step calculation is also very clear. I could follow each stage from the raw bearings all the way to the final displacement without getting confused. One thing I think could be stronger is your diagram. From what I can see, the diagram 2 shows the vector and the resultant, which is good. But the angle values and the east and north component levels are not written directly on the diagram. So, if you added those levels inside the diagram itself, the reader will not need to go back and forth between the diagram and the calculation to understand what each arrows represents.
Okay, I also want to add one more strand. You made a very clear distinction between total distance, which is 12 kilometer, and actually displacement, which is 10.44 kilometers. That is a key concept in a vector, and it is not always easy to explain. Simply, you did it well. Many people get confused between those two ideas, and your report addresses that gap directly. For improvement, I think your advantage and limitation section could go deeper. You mentioned that the model assumes flat terrain, which is correct, but you could also talk about how even a small error in the compass reading, say just 2 or 3 degrees off, could lead to significant positional error over 12 km. That kind of specific example would make the limitation feel more realistic and connected to the actual calculation.
Okay, thank you Nuris and Adib. You are both right. I will go back and add proper labels to diagram 2, including the angle values and the east and north component, so everything is visible directly on the diagram. I will also expand the limitation section to include a concrete example of how a small compass error affects the final result. These are very practical suggestions, and I can see exactly how they would improve my report.
Thank you, Nuris and Khayra. My topic is about how vectors are used in precision agriculture, specifically to track and control the movement of GPS equipped fertilizer truck on oil pump station. The problem began when uneven fertilizer distribution was happening across the plantation. This was caused by pressure imbalance in the piping system and inconsistencies in how the GPS truck was moving. To solve this, a second piping system was added, and the truck was assigned to travel between the two systems to distribute fertilizer more exactly. Okay. So, based on the GPS record, the truck moved 600 meters toward the west and 800 meters toward the north. I express this as a position vector equals 600 plus 800j since the starting point is the origin. The displacement vector is the same as the position vector equals 600i plus 800j. You can see, Khayra? Yes, okay. To find the shortest straight line distance, I use the magnitude formula, the square root of 600 square plus 800 square. That gives the square root of 360,000 plus 640,000, which equal the square root of 1 million, which is exactly 1000 meter for the direction. I use the tangent formula. Tangent theta equals 800 over 600, which gives theta equal 53.13 degree north of east. So this is direction for the truck is moved to the second piping. I also calculate the unit vector by dividing the displacement vector by its magnitude u. That's equal 600 plus 800j divided by 1000, which give 0.6 plus 0.8j. The unit vector represent the direction of the movement without any magnitude, which is useful for automated steering control. So finally, I apply a first vector calculation. So the truck engine produce 5,000 Newton and the friction force is 1,200 Newton. The net force is therefore 3,800 Newton multiplying by the unit vector. The force vector is F equal 3,800 times open bracket 0.6 0.ci plus 0.8j close bracket, which is F equal 2,218 plus 3,040j. So as you can see from the picture. Okay, so the main advantage is that this allows the truck navigation system to adjust its speed and steering in real time based on the vector data. The limitation is that oil palm trees can obstruct GPS signal, and the real path through the plantation cannot be a perfect straight line because of the tree trunks. That is my presentation.
Thank you, Adib. One thing that I think really stood out in your report is that you went further than just displacement. You also calculated a force. Vector which none of us covered. That shows a more complete picture of how vectors work in a physical system, and not just where something moves, but what forces are acting on it. I thought that was impressive. One area I think you could improve is your direction calculation. You use tangent theta equals 800 over 600, which is correct, but in your diagram, it is not clearly shown which side of the right angle triangle is the opposite and which is the adjacent. A reader who is not very confident with trigonometry might wonder why you put 800 on top and 600 on the bottom. Adding a simple label or short explanation in the diagram will make that so much better.
Okay. Thank you, Nuris. I completely agree about the diagram. Another strength I want to mention is how your report connects the mathematics to Industry 4.0 technology. You mentioned IoT sensors, GNSS navigation, and real-time data analytics. Those are all very current and relevant reference. It shows that you researched beyond the textbook and thought about how this problem fits into modern agriculture engineering. For my suggestion to improve your work is the unit vector section. I think you can correctly calculate it as 0.6i plus 0.8j, but you only wrote one sentence to explain it. I think you could add a clearer explanation of what the unit vector is actually used for in practice. For example, how the navigation system multiples in the unit vector by different net force values to control the truck direction at different points along the road. That would make the unit vector feel more connected to the real problem.
Okay, thank you for your suggestion. I will update the direction diagram to clearly label which side is opposite and which side is adjacent. So the reasoning behind the tangent formula is obvious to any reader. I also agree that the unit vector section is too brief. I will expand it to explain specifically how it is used to control the truck steering in the navigation system. Your feedback was direct and helpful. I know exactly what to fix now. Thank you for Khayra and Nuris.
Okay, so good job for all three of us. So we have now finished all three presentations and given feedback to each other. Before we close, I would like each of us to share one reflection, something you learned from today's discussion, or something that surprised you. For me, what stood out was how different our three topics are, yet they all use the same core idea, that a vector has both a magnitude and a direction, and that this combination is what makes it useful. Whether it is an electric field in a phone screen, a hiking route through a forest, or a fertilizer truck in a plantation, the mathematics behind it is the same.
Oh, I find Nuris' presentation is really eye-opening for me. I knew that the touchscreen detects touch, but I had no idea that it involved 4 different types of vector operation at the same time. It made me realize that vector mathematics is embedded in every technology that we take for granted. It also made me think more carefully about how I can make my own report stronger, especially the diagram and the limitation section, based on the feedback I received from both of you.
Okay, listening to Khayra hiking example helped me see my own work differently. We both use displacement and magnitude calculation, but she used trigonometry with compass bearing, while I work directly with x and y coordinate. It is interesting how the same vector tools can be applied in a very different way. I also appreciate the feedback about my unit vector section. I realize now that I explained the result but not the result behind it, and that is something I will fix. Sorry.
Okay. So thank you, Khayra and Adib. So I think all three of us have gained something useful from this session. Not just feedback on our own reports, but also a broader understanding of how widely vectors can be applied in real life. That is exactly the point of this assignment. I hope we all feel more confident about our final submission. That is the end of our 30-minute group discussion for assignment 2, task 2, MTES1104. MTES1104 Algebra. Thank you very much.
Bye.
Bye.